You might be wondering why I am starting with this odd looking graph. Well, this is to say why maximum power point tracking system is necessary to connect with a solar panel. The green line is showing the variation of voltage when we increase the current of a solar panel, and the red line is power versus current. Power is nothing but voltage multiplied by current. When we start to increase the current of a solar panel, power also increases and reaches a maximum value for a certain amount of current. But if we increase the current further, the power will decrease. What happens in this region? The major part of the power the PV panel is generating is getting dissipated on the panel itself. So definitely we won't like to operate the solar panel in this region. On the other hand, if we operate in this region, we are not enabling the PV module to generate the maximum power in the particular condition. So to fully utilize our solar panel's capability, we would like to operate it in this MPP, which is not too much difficult than dancing on the head of a needle. This is because we don't know exactly at which current or which voltage we will reach this point. And also the point keeps shifting depending on the sunlight, panel temperature, weather condition and other factors. There are many algorithms to track the maximum power point, but discussing them all would be enough to turn this video into a boring lecture. I will only discuss the method I have used in this project, and that is hill climb. In this method, microcontroller first guesses a base power and starts to increase the current. As current increases, power also increases, and it keeps increasing, reaches the maximum power point, starts going down the maximum power point, but microcontroller keeps increasing the current until the power goes below the base power. Once it goes below the base power, it starts decreasing the current, and it keeps decreasing until it goes below the base power on the opposite side of the maximum power point. And again it flips over and starts increasing the current, and this happens over and over. At the same time, the base power also lifts up, and eventually the base power reaches slightly below the peak power, and the operating point keeps hovering on this narrow region. For DC-DC conversion, I have used buck boost converter here. The duty cycle is controlled by the Arduino itself. This op-amp configured in differential mode is used to feed back the output voltage, but sensing the output current wasn't that easy, and that's why I had to use these two PNP transistors. Diodes D1 and D2 are used to bias them with a fixed emitter current. At no load condition, the potentiometer R29 is adjusted so that the potential drop across R25 and R24 becomes equal and op-amp output becomes 0. But as the current passes through the shunt resistor R28, current increases through transistor D2. The potential drop on R24 and R25 are no longer equal, and that potential difference is amplified by this op-amp, and the load current feedback signal goes to the microcontroller. In the code, there are two different control algorithms. One is controlling the charging current and voltage, while another part is tracking the maximum power point. At the beginning, the P base is initialized with a small value. Every 100 milliseconds, the power will be compared with the base power, and if it is less than the base power and the toggle flag is reset, then the direction of the duty cycle change will be set to positive if the voltage has been increased, and the duty cycle change direction would be set to negative if the input voltage has been decreased. The toggle flag is set to prevent the alternation in duty cycle change direction until the power goes above the base power. The maximum allowable duty cycle is increased or decreased by a small step depending on whether the duty is positive or negative. The base power is incremented or decremented by small steps every 2 milliseconds and tries to remain at a position slightly less than the peak power, called hysteresis. The hysteresis value should be adjusted carefully. If it is made large, then the power will hover over a wide region and we will observe a big fluctuation in the output. On the other hand, if we set it too small, then microcontroller won't be able to lock itself in the position over the base, and starts hovering between the open circuit point and the short circuit point. In my case, I got a stable output with 50. Rest of the code is self-explanatory and I'm not going to discuss those. I have uploaded the code along with the circuit diagram into the GitHub repository. The link is given in the video description below. I soldered all the components on a pref board according to the schematic. Unfortunately, I don't have a solar panel right now, so to emulate a 12 volt 10 watt solar panel, I built this highly complicated aerospace grade circuit according to this schematic. From the simulation result, the open circuit voltage is 22.4 volt, short circuit current is 0.751 ampere and the maximum power is 13.03 watt. Here I am using a series of two 12 volt batteries and 4 diodes in series. To obtain an open source voltage of around 22.8 volt. And short circuit current is 0.74 ampere. Both are very close to what we got in our simulation result. So we are supposed to get a maximum power of around 13 watt. Let's see what does our controller do. But before starting the test run, I calibrated 4 coefficients to get the current and voltage readings of input and output correctly. Nevertheless, all my efforts proved to be failure to get a near reliable reading for the output current. Luckily though, the MPPT algorithm relies on the input current and voltage readings, both of which were being sensed somewhat okay. So I moved on, connecting a multimeter to measure the output current. Here I am going to charge this small 12 volt lead acid battery. Turned on the source. At the beginning, input power is hovering between the open circuit point and the short circuit point, and very soon it became stable at around 18.4 volt and 0.71 ampere, which means around 13 watt. Remember, we got 13.03 watt is the maximum power from the simulation result, so our MPPT controller is definitely working. Unfortunately though, I cannot say that this was a successful project because the efficiency of the buck boost converter is terribly low, only around 70%. Also, I want to integrate IoT and increase the current capacity to at least 6 ampere. But I am so tired in modifying the code over and over to get a rather stable output, and I also modified the circuit many times in between. So for now I want to leave this project for a few days, and probably I will be able to complete this project in near future. That's it for this video. Thanks for watching and I hope you have liked it. If so, please give it a like and please consider supporting me by subscribing this channel. I will come again soon with more interesting videos.